Hello everyone and welcome back to another video. Today we're going to talk about rational operations and equations. Before we get started with the 20-1 content, we're going to go ahead and review some of the content from previous grades. First off, taking a look at the idea of rational numbers, they are really just any number that can be written in the form of a fraction. So for example, we have a over b, where b cannot equal to 0. And a and b are just going to be any integers. So for example, we could have -4 over 7, we could have 2 over 5, and so on. Again, our denominator, or the number on the bottom here, cannot be equal to 0 because we already know that we can't divide by 0. So when we're trying to figure out equivalent forms of rational numbers, we want to go ahead and try to simplify each one of these. So for example, we know that 10 over 20 is the same thing as 5 over 10, which can be further simplified to 1 over 2. This would be considered a fraction in lowest terms. For this first set of examples, there's a couple different things we can do. If we look at 12 over 28, let's go ahead and type that in, 12 over 28. And we have an answer of 0.4285. We want to turn this into a fraction in lowest terms. So what your calculator does, or at least on the Casio, all I need to do is hit this FD button. So basically it turns that decimal into a fraction and vice versa. So we know here that this 12 over 28 is the same thing as 3 over 7. If you are on a TI 83 or 84, all we need to do is once you type in that 12 over 28, you're going to hit the math button, which should be located right about here. And you're going to just use that first option, which is going to be fraction, so math, and then just enter on that first option, which is fraction, and you should see this decimal turn into 3 over 7 as well. Alternatively, if you want to challenge yourself and do a little bit of mental math, really all we're trying to do here is we're trying to rewrite both our numerator and denominator so that we have the same factors appearing. So for example, we know that 12 and 28, the largest number that can be used to divide both of these is going to be 4. So I'm going to rewrite this as 4 times 3 over 4 times 7. Oops, let me clean that up a little bit. So 4 times 3 over 4 times 7. Now, really what we can do is we can actually rewrite this as 4 divided by 4 times 3 over 7. Well, and we know that 4 divided by 4 is really just 1. So we have 1 times 3 over 7, which is just 3 over 7. So that's really what's happening if your teacher has ever told you to divide the top and the bottom of your fraction by the same number. We're just trying to factor out a common factor. Let's go ahead and do the same thing for the next couple of examples here. So we have -15 over 35. And we get that decimal. I can go ahead and turn that into -3 over 7 once again. So -3 over 7. And then last but not least, -24 over -60. We know that when we divide two negative numbers, we're going to end up with a positive number. So -24 over -60. And we end up with 0.4. And if I turn that into a fraction, I get 2 over 5. Next up, we're going to try to figure out where the error occurred in this next solution here and come up with the correct solution. So here we can see that we've crossed out the 12 and the 4, and we see that a 3 and a 1 have taken its place. We can see pretty quickly that whoever did this question has divided the 12 by 4 and the 4 by 4 to give you the 3 and the 1. But what they've essentially forgotten to do is apply the same idea to that -1 there. So really, this is where that mistake is going to happen. They forgot about that -1. And there's really two ways that we can think about this problem. The quickest way to do this is really just to apply the rules of BEDMAS, 12 minus 1 first, divided by 4, and this gives us 11 over 4. So we definitely won't end up with 2 as an answer. Alternatively, we could also do this. Because we know that we have 12 minus 1 over 4, we can actually rewrite this as 12 over 4 minus 1 over 4. And when I subtract fractions with the same denominator, I'm simply just going 12 minus 1, which is 11, and I get 11 over 4 as well. The next thing we're going to take a look at is how to multiply and divide rational numbers. So if we're looking at two rationals being multiplied with each other, we have A divided by B, and we're going to multiply this with C over D. So really our product, once we multiply these two fractions together, is going to be A times C over B times D. So in example number 1 here, we can see that we have 3 times 2. Let me write that a little neater. 3 times 2 divided by 4 times 12. And we end up with 6 over 48. And we can cheat, use our calculator a little bit, and we get 1 over 8 as our answer. Again, another way that we could essentially do this if you don't want to utilize your calculator too much is, again, we can look for some of those common factors. So what I like to do in my head is I like to think, well, I see a 3 and a 2 up top. I can't divide them by anything else. I've got a 4 and a 12 on the bottom. So what I'm going to try to do is rewrite the bottom so that I have the same factors on the top as I do on the bottom. So because of this 2 here and this 4 down here, I can see that I can actually rewrite this 4 as a 2 times 2. So I have 3 over 2 times 2. And now I've got that 2 on top there. I want to try to rewrite this 12 using a 3, and I actually end up getting 3 times 4. And based off what we've done previously up here, again, because we're trying to get rid of those common factors, if I see the same factor on the top as I do on the bottom, I can start to essentially get rid of them. So here we see that we've got a 3 on the top, 3 on the bottom. I'm going to get rid of those. I've got a 2 on the top and a 2 on the bottom, and I'm going to get rid of those. It's not a 0 left on top. We don't suddenly end up with 0. We really have times 1 all the time. And we can see that we have now 1 over 2 times 4, which really just gives us 1 over 8 yet again. So this is just an alternative way of doing it. I wouldn't recommend actually writing it out all the time like this because it does become a little time consuming when you start to work with more complex problems. But that's just one way for us to visualize exactly what's happening. If you look at our calculator here, we want to make sure that we're utilizing best practice when it comes to working with our calculators. We want to use brackets whenever we can. So 3 over 4, we're going to go ahead and put that inside of brackets, just like that. And then times 2 over 12, just like that. And we get 0.0 or 0.125. And we're going to convert that into a fraction rather. And we get 1 over 8. Let's try out the second problem here. So we've got 6 over 7. Let's put that in brackets, 6 over 7 times 1/2, and then times 14 over 3. And we end up getting an answer of 2, which again, we don't really need to simplify too much. So let's go ahead and just write 2. Next, if we're trying to find the quotient of each expression here, we just want to recall our rules for dividing fractions. So let's say we have A divided by B, and that fraction is divided by C over D. This is really the same thing as taking the original first rational here, and we're going to now multiply by the reciprocal. Okay, so basically what we're doing here is we're multiply by the reciprocal. And remember, the reciprocal of a fraction is essentially what it looks like is we're just flipping that top and that bottom, the top number and the bottom number, so your numerator and your denominator. So if we have C over D, the reciprocal of that is D over C. And really the way that reciprocals work, if I give you guys an example, if I take 2 over 3, the reciprocal of this is going to be 3 over 2. And it's called the reciprocal because if I were to multiply these two fractions together, we'd end up with 2 times 3, which is 6, and 3 times 2, which is 6, which just gives us 1. So the reciprocal of some sort of fraction really is just whatever other fraction you need to make that product equal to 0. So going ahead and working through this first problem here, we've got 4/3. We're going to multiply by the reciprocal of this second rational, and that 2 over 12 now becomes 12 over 2. And we can see that we've got 4 over 3 times 12 over 2, a couple different ways we can do this. We've got 48 over 6, and 48 divided by 6 just gives us 8. Taking a look at the second problem, again, we've got 12 over 15. We take our original first fraction, and we're going to now multiply it by the reciprocal of this second rational. So that gives us 9 over 10. So let's try it out on our calculator. We've got 12 over 15. Oops, 12 over 15. And we're going to multiply this with 9 over 10. We get 0.72, and we turn that into 18 over 25. So 18 over 25. Now moving on to adding and subtracting rationals, this is where it gets a little bit dicey for some of you guys. So the important thing to keep in mind here is that we want to make sure that your denominators are exactly the same. So denominators must be the same. So what that's going to mean is whenever we have the same denominators, we can simply just add or subtract the top here. So for example, number 1, because our denominator of 3 is already the same for both rationals, we can go ahead and just add 1 plus 1, which gives us 2. For number 2, it's not quite so easy because now we have different denominators. And what we're trying to do is we're trying to find whatever our lowest common denominator is. And in this case, between 2 and 3, 6 will be our LCD. So we need to ask ourselves, what do I need to multiply the top and the bottom by for each fraction to make sure that our denominators will be the same? So to get a denominator of 6, we need to multiply the bottom here by 3. And what I do to the bottom, I also do to the top. And I'm going to do the same thing with the fraction on the right. So here, to turn that 3 into a 6, I'm going to multiply it by 2. And what I do to the bottom, I do to the top. So what does this leave us with? We'll have 3 times 1, which gives me a 3. 3 times 2, which gives us a 6. And we're going to subtract 1 times 2, which is 2. And then 3 times 2, which is 6. And now because our denominators are the same, I simply subtract the top, 3 minus 2, which gives us 1. And I get 1 over 6. Again, what we can do with the help of our calculators is we can go ahead and just type it in ourselves to double check. So I got 1/2 minus 1/3, and that gives us this decimal, and simply pressing that button there, we get 1 over 6. Let's take a look at the third example, and we can see here between 4 and 6, our LCD is going to be 12. Now, some of you guys might be wondering, well, what happens if I don't actually find the lowest common denominator? I just find a common denominator. So let's say we decide to go with 24 instead. Really, all that means is we're just going to have an extra step at the end of the day. So I'll show you that first before I actually solve it. So here, let's say we want 24 on the bottom. I'm going to multiply this by 6, multiply this by 4. And what I do to the bottom of both, I'm going to do to the tops as well. So this gives me 6 over 24 minus 20 over 24. And now I have the same denominators. So that gives me 6 minus 20 up top. So I get 14, or negative 14 rather, negative 14 over 24. And I can divide out a 2 from both the top and the bottom of both of these. And I end up with negative 7 over 12. So you can see that eventually we do end up with a denominator of, or lowest common denominator of 12. But really we just add one additional step. So let's go ahead and erase this. So now working with 12 as our lowest common denominator, I'm going to multiply this bottom by 2, multiply the top by 2 as well. Oops. Multiply this one by 3 on the top, and I'm going to multiply by 3 on the bottom. This gives me 3 over 12, and I'm going to subtract 10 over 12, and that leaves me with negative 7 over 12, just like we had earlier. We just have one less step. In this last example, our LCD in this case is going to be 40. Again, how do I do that so quickly? Again, it's a lot of practice, understanding how numbers work in terms of mental math, and just knowing what numbers are divisible, or what's the smallest number that can be divisible by both of your denominators is really important. And again, it's not a huge deal if you don't get the right denominator. It just means they're going to have an extra step at the end of the day. So starting off with the left-hand side, I'm going to multiply this by 5, multiply the top by 5 as well, multiply this by 4, multiply the bottom by 4, and we end up with 15 over 40 plus 12 over 40, and that gives me 27 over 40. And again, if you're a little bit unsure if you've simplified it all the way, you can always use your calculator to double check. we end up getting 3 over 8. And we're going to add that to 3 over 10. Oops, too many ones. And we get that decimal, and we turn that into 27 over 40. So we can't simplify that any further, as you can see. So if you're able to, feel free to use your calculator to double check your work. So for the next two, we're going to try to figure out what the errors are in each solution and then show the actual solution. So for these types of problems, I do like to kind of give you the idea of, well, why can't we just subtract the denominators just like we do with the numerators? So typically when students make mistakes here, they'll have 3 minus 1 gives you a 2, 4 minus 2 gives you 2, which ends up with a 1 here. And just to illustrate, because I love pizza, I'm going to use pizza as my example here. So we've got 3/4 of a pizza. So I've got these 3 slices. I know I'm not very good at cutting pizza. So I got 1, 2, 3 slices of pizza there. And we're going to subtract 1/2 of the pizza. So we can see that if I were to cut this again in quarters, we would essentially just be taking away these 2 pieces. So we're taking away 2/4 essentially. And we can see that's, it's about the same as what we do with that pizza on the left-hand side. And we can see whatever's left over is just going to be that 1/4, right? So we should end up with 1/4 as an answer, not one whole pizza. Okay, so we can already see just visually that it's going to be incorrect. So working through this and making the right adjustments, we know that 3 over 4 and 1 over 2, we need to make sure we have the same denominator. And that denominator is going to be 4. So we have 3 over 4. And we're going to multiply the right-hand side by 2 on the top and 2 on the bottom. So that gives me 2 over 4. And we end up with 3 minus 2 gives us 1. And the 4 stays the same. And we get 1/4 just like we expressed earlier. For this problem, we can see that what they've done is they've tried to just get rid of a common factor on the top and the bottom, which is very incorrect. So again, we're going to start by finding our common denominator. So let's go ahead and rewrite this. 5 over 3 plus 3 over 8. Our common denominator between 3 and 8 in this case is going to be 24. So let's multiply this by 8 on the top and the bottom. Let's multiply this by 3 on the top and the bottom. And we end up with 40 over 24 plus 9 over 24. Then adding our numerators together, we end up with 49 over 24. So here is where the actual content from Math 20-1 comes in. So starting off with what a rational expression is going to be, it's really just an algebraic fraction where your numerator and your denominators are going to be polynomials. So now that just means that we can have a mixture of just constants. We can have a mixture of a term that has both a coefficient and a variable, or we can just have variables on the top and on the bottom. So to get us warmed up, we're going to go ahead and evaluate some rational expressions with some of the values that are given here. So given the expression 6 over x, we're going to plug in the values of 2, 0, and 1 into each of these, and we're going to see what the results are. So first of all, when we have x is equal to 2, it's now going to be 6 over 2, which gives us 3. Pretty straightforward. Let's skip ahead to this one here. If I have 6 over 1, that just gives me 6, nothing too crazy. Now when we look in the middle where we have x is equal to 0, well, we have 6 over 0. And if we were to punch that into our calculator, 6 divided by 0, it's going to give us some sort of error. And you might think, well, maybe I just punched it in wrong. I'm going to try it again. Maybe I'm supposed to use brackets or something. 6 divided by 0. That's not going to really change anything. We're still going to end up with an error. So again, just to give you a refresher, the simplest way to kind of show why dividing by 0 gives you an error, or really we call it undefined. So I'm going to go ahead and write that down, undefined answer. So we don't have an answer, it's an undefined value. The simplest way to kind of think of it is, let's say we have 25 divided by 5. That gives me 5. So what this kind of implies is that 5 times 5 then gives me that number that's back on top. If I multiply this denominator with that quotient there, 5 times 5 gives us 25. That's something that works. 10 divided by 2 is equal to 5. So that means that 2 times 5 is equal to 10, and that works. Well, let's imagine that we have 10 divided by 0 is equal to some number x. We don't know what that number is. Well, for this to work, 0 times x has to equal to 10. Well, the problem is that there are no defined values to make this work. Okay, we can't multiply 0 by anything to make it equal to 10, so we call that undefined. So therefore, trying to divide by 0 is what we call undefined. So I'll work through some of the tougher ones here. Let's go ahead and take a look at something like this. 2x minus 2 divided by x squared minus 3x plus 2. So we're going to substitute in a 2 every time we see an x. So we have 2 times 2 minus 2. And we divide that by 2 squared minus 3 times 2 plus 2. And this leaves us with 2 divided by 0, which means that we have an undefined answer. So undefined. Taking a look at this middle one, we have 2 times 0 minus 2 divided by 0 squared. A little messy there. We're getting a little bit tight on space. Minus 3 times 0 plus 2. This leaves me with negative 2 over 2, which gives us negative 1 as an answer. Last but not least, let's see what happens when we have x is equal to 1. So I have 2 times 1 minus 2 divided by 1 squared minus, this is going to be minus 3 times 1. And then this is going to be plus 2. This gives me 0 divided by 0, which again leaves me with an undefined. So something we're going to touch on in just a little bit is what do we call these numbers that when we put them underneath into our numerators, or into our denominators rather, what do we call them? So basically in each one of these cases, when we have x is equal to 0 for this expression, when x is equal to 2 for this expression, and then when x is equal to 1 for this expression, these undefined values really call these non-permissible values. So let me write that in black, non-permissible values, otherwise known as NPVs. So we're going to touch on it in just a little bit, but essentially non-permissible values, or NPVs, are really just whatever numbers we put into our denominators that make it equal to 0, which essentially just breaks mathematics for us. So at this point, I would recommend that you pause the video and try to evaluate each one of these expressions. I'll just write the answers down, but you should go ahead and unpause once you're done and double check your work to make sure that you found all of the non-permissible values. So for this next section, we're going to focus on non-permissible values, or NPVs. But before we get into it, I just want to remind you that factoring is going to be a massive deal when it comes to this outcome, because there's going to be so much factoring involved. If you need to review some of those factoring methods, you can feel free to check out some of my previous videos that I'll link up in the top right of your screen. So let's get right into it. NPVs, or non-permissible values, we just say that really, first of all, that a fraction won't be defined when your denominator is going to be 0, because we can't divide by 0. So essentially those NPVs are really just values that make your denominator equal to 0. So we call anything that makes your denominator equal to 0, we call those NPVs. So the key to figuring out what those NPVs are is we're just going to equate whatever your denominator is, make those equal to 0, and solve. Now, the part to keep in mind is sometimes they are going to be single terms like this, are going to be monomials. They could be binomials. They could be things that we need to factor out. So we're going to go ahead and see how we would work with these NPVs. So in this set of practice, we're going to figure out which value of the variables here, won't be defined for our rational expression. So here we have a single variable on the bottom, n, and really the only thing we need to keep in mind is that n cannot equal to 0. So that's going to be our NPV for this case. Next, we notice that we have a binomial on the bottom, a minus 4. So we have a minus 4 cannot equal to 0. Note that we don't really look at the top at all. We're only worried about what's on the bottom, your denominator. So to get a by itself, I'm just going to add 4 to both sides. So I'm going to go plus 4 on both sides. So plus 4 and plus 4. And we end up getting a cannot equal to 4. And again, if we put in a 4 in here, 4 minus 4, that gives me a 0, which helps us prove that 4 is indeed an NPV. In question C, this is where a little bit of factoring comes into handy. We can recognize the bottom here, x squared minus 9, is really just a difference of squares. So I can actually rewrite this as x divided by x plus 3 and x minus 3. So x plus 3 and x minus 3 go on the bottom. Now, essentially what we can think of this as is we could have something like x divided by a times b. X can really be anything. I don't really care what x is, but a and b are going to be the problem. If we're trying to avoid dividing by 0 here, it means that we want to take care of two factors. In this case, a cannot equal to 0, and our second factor, b, cannot equal to 0. So what am I trying to get at here? Well, same thing occurs here where I actually have two factors. I have x plus 3 and x minus 3 as my two factors on the bottom. And that's what we're going to keep in mind as we find the NPVs for these two. So looking at our green factor first, we have x plus 3 cannot equal to 0. So we can go ahead and subtract 3 from both sides. And we get x cannot equal to negative 3. For our factor here in the blue, we have x minus 3 cannot equal to 0. Let's go ahead and add 3 to both sides. And we get x cannot equal to positive 3. So we have two NPVs, which is totally okay, right? Because if I put a negative 3 into both of these, I'll end up with 0 times negative 6, which leaves me with a 0 on the bottom. If I put a 3 into here, I'll have 6 times 0, which is still going to be 0. So negative 3 and positive 3 will be my two NPVs. For this next one, it's going to be a little bit more complex because we're now looking at a trinomial or a simple trinomial where a is equal to 1. So we're just trying to look for two numbers that multiply to negative 4 and add up to negative 3. And I can simply factor this as x minus 4 and x plus 1. Okay, and again, like I said, we're trying to look for two numbers that multiply to negative 4. So negative 4 times positive 1. And they add up to give me negative 3. So this is going to be a simple trinomial where I can just factor it like so. And again, we're going to end up with two NPVs. First off, I have x minus 4 cannot equal to 0. So x cannot equal to positive 4 is my first NPV. And then for my second NPV, I can state that x plus 1 cannot equal to 0. So x cannot equal to negative 1. And once again, I end up with two NPVs. This next one's going to be a little bit tricky, but really it's not too bad. We start off with saying that x times y cannot equal to 0. Let me change that a little bit. X times y cannot equal to 0. So the only way that we end up with a product of 0 when we multiply the two together is one of two situations. We get x cannot equal to 0. So if x is 0, that doesn't work. And our second situation is that if y was 0, that would make it 0. So we can state that x and y both cannot equal to 0. This next one here, once again, taking a look at the denominator, x minus y cannot equal to 0. Let's add y to both sides. So x cannot equal to y. And we can't actually go much further than that. Just those two cannot be the same number, no matter what. This next one, once again, looks a little bit tricky, but same idea. 8x minus 10y cannot equal to 0. So we're going to end up with two NPVs here, one where we are solving for x and one where we're solving for y. So first off, let's add 10y to both sides. Let's divide both sides by 2, so that leaves me with 4x cannot equal to 5y. Then we divide both sides by 4, so x cannot equal to 5 over 4y. That's my first NPV. Then for my second NPV, really I can actually just start off from this stage right here. So starting off from here, 4x cannot equal to 5y. I can just divide both sides by 5 and I get 4 over 5x, or y cannot equal to 4/5 of x. So I end up with two NPVs once again. So here we're going to start simplifying rational expressions. Essentially what we're going to try to do is find the GCF, or greatest common factor, and then divide both your numerator and your denominator by it. So for this first example, I'm going to divide both the top and the bottom numbers by 12. So divide the top by 12 and divide the bottom by 12. So that leaves us with 24 over 12, which is 2, and 60 divided by 12, which is 5. And we don't have any NPVs here since we have no variables in our denominator. For the second example, we notice that we have BD over BE. We have the same factor on the top and the bottom. But before we do that, let's go ahead and write down our NPVs. So we see the bottom here, we have BE cannot equal to 0. So that means we have two situations, B cannot equal to 0 and E cannot equal to 0. So we've got two NPVs here. And once we have those down, we can go ahead and get rid of our common factors, B on the top, B on the bottom. So that means that my final answer is D over E, with my NPVs of B cannot equal to 0 and E cannot equal to 0. For the next example, let's look at our NPV first. We have 12x cannot equal to 0. So x cannot equal to 0. I can just divide both sides by 12. So I get x cannot equal to 0. Now we can reduce our coefficients here. So 6 and 12 can both be divided by 6. So this leaves me with a 1 on top and a 2 on the bottom. I can get rid of an x on the top and the bottom, and I am now left with y on top, 1y, or just y. So let me undo that. So I have y on top, and I have a 2 left on the bottom. So I have y over 2 with my NPV of x cannot equal to 0. For this next one, let's start with NPV first. 35x cannot equal to 0, so x cannot equal to 0. And now I can divide our coefficients, divide the top by 7 and divide the bottom by 7. That leaves me with 3 and 5. I have an x squared on the top and an x squared on the bottom, so I can actually think of it like this: x times x, x times x on the top divided by x. Really all we're doing is we're getting rid of an x on the top, x on the bottom, and we're left with an x. So here we're getting rid of one of the x's on top, one of them on the bottom, and now we're left with 3x over 5 with my NPV of x cannot equal to 0. For this next one, we've got a tricky looking denominator, but it's really not that bad. 14a cubed b to the power of 8 cannot equal to 0. The only way that this whole left side is going to equal to 0 is if a is equal to 0, so a cannot equal to 0, and b cannot equal to 0. Those are going to be the two NPVs in this case. So in terms of our expression, I can divide both the top and the bottom by 2. That leaves me with 1 over 7. Here I can get rid of 3 a's from both the top and the bottom. So I'm going to get rid of the 3 down there. This becomes a squared up top. So let me write this down before we forget. So I have an a squared on top. And then on the bottom so far, we have a 7. And there are no more d's on the bottom. And then next, I've got 7 b's on top, 8 on the bottom. So I can get rid of all 7 on top. And I'm left with a single b on the bottom. So a squared over 7b is my final simplified rational expression. All right, before we get started with this next section, I just wanted to take some time to look at the difference between working with fractions on a Casio calculator versus a TI-84. So as an example, let's go ahead and type in maybe let's say 24/36 onto our Casio, and we end up with this repeating decimal. And all we need to do to turn this into a fraction is to hit this FD button, and we end up with 2/3, just like that. So once again, we type in whatever fraction we want to start with. We end up with a decimal here, and we can go ahead and press FD, and we get 2/3. Switching over to the TI-84 here, we can do the exact same thing, 24/36, and we end up with the same decimal, except in this case, now we're going to hit the math button, which is located right underneath alpha. And you can see here that we're already on the fraction button. So from here, we're going to hit enter. And it's saying to turn your previous answer into a fraction. So once we're there, we can go ahead and hit enter, and we end up once again with 2/3. We can start off with whatever decimal we want. Let's say, for example, we have 1.5, and we can press enter. Once again, press math and enter to go to fraction. And we turn that 1.5 into a fraction, which is 3/2. Same thing with the Casio. I can just go ahead and type in 1.5, and I'm just going to hit FD to turn this into 3/2. So just so you have an idea of how to work out fractions on both the TI-84 and the Casio. So now when we're looking at examples where you have a binomial or trinomial as part of your expression, we need to be able to factor out some common factors and be able to get rid of them. Now, before we can get rid of them, we also need to make sure we take those NPVs first. So looking at this first example, we can see that we can factor out a y from both terms on the top. So we've got y, and then 3y plus 5 is what we're left with up top. And then we have a 2y left on the bottom. So in this case, we're going to look at our NPV. We can see here that our NPV comes from 2y. So 2y cannot equal to 0. Divide both sides by 2. And we can see that just y cannot equal to 0. And that's going to be our NPV. So from here, we can go ahead and get rid of our common factors. So I can get rid of a y on the top and a y on the bottom. And we are left with 3y plus 5. And let me clean up that y. 3y plus 5 divided by 2 is our simplified form. For the second example, we'll notice that we need to factor out the bottom here. So the 3x squared can stay the same up top. On the bottom, we'll notice that we can factor out a 6x. And we're left with 2x plus 1 inside of the brackets here. And from there, we have two NPVs, one coming from the 6x and the second one coming from the 2x plus 1. So from here, let me see if I can find some room. With the 6x, we know that 6x cannot equal to 0, so x cannot equal to 0. That's our first NPV. And then for the second one, we have 2x plus 1 cannot equal to 0. 2x cannot equal to -1. So let's divide both sides by 2. So x cannot equal to -1/2 will be my second NPV. So from here, we're going to get rid of some common factors. We can see that we've got an x squared up top and an x on the bottom. So I can get rid of one of the x's on top and one on the bottom. From here, I can simplify the 3/6. I can divide a 3 out from both the top and the bottom. So I'm left with a 1 here. And then on the bottom, I have a 2. So that means that I am left with just an x up top, or 1x, divided by the 2 on the outside, and then a 2x plus 1 inside of my brackets there. For this last one, it's a little bit tricky, and one that students will typically have a lot of trouble seeing. So I'm just going to put a little star beside this one so we can highlight it. So the difference between the top and the bottom, your numerator and your denominator, is we'll notice that the signs for each of these terms are flipped. Here you have a +5, here you have a -5, up top you have a -x, and then on the bottom you have a +x. The quickest way to look at this type of problem is to be able to factor out a negative from your terms up top. So if I factor out a negative from the negative x, I'm left with a positive x now. And if I factor out a negative from the positive 5, I end up with a negative 5. So you can see here, if I were to distribute this, negative 1, there's an invisible 1 right there, negative 1 times x gives you negative x, and negative 1 times negative 5 gives you a positive 5. And now we can just divide this by x minus 5. Before you move any further, we can look at our NPV. So we have x minus 5 cannot equal to 0. Well, let's add 5 to both sides. So we get x cannot equal to positive 5 as our NPV. Once we get to this stage, we can go ahead and get rid of our common factors. So we have an x minus 5 on top, x minus 5 on the bottom, and we are simply left with negative 1 as our simplified form. In these next two examples, we'll notice that we need to factor both the top and the bottom. So being able to recognize certain factoring methods is really key to this section. So looking at our first example, we have a difference of squares up top. I can recognize this because 16x squared is a perfect square, 25y squared is a perfect square, and we have a subtraction sign in the middle. So this is a difference of squares. So I can factor out the top as 4x minus 5y times 4x plus 5y, and that's going to be up top. And then here on the bottom, I can factor out a 2, so I'm left with a 4x minus 5y on the bottom. Now, once I've got to this stage, I can look at my NPVs from the bottom. So here I have a 4x minus 5y cannot equal to 0. So 4x minus 5y cannot equal to 0. So I get 4x cannot equal to 5y. So I'm happy if you guys leave it like that. We can go ahead and move it so that we are isolating for a certain variable. So we can take this in two directions. Let's go ahead and maybe I'll move this expression down here. So if we were to solve for x, in this case, we get x cannot equal to 5/4 y. So that's the first one that I can look at. And then I can also isolate for y. And basically, I'll say that y cannot equal to 4/5 x. So either way, we have those two NPVs, or we can have more of a general statement like this one up top. So once we get to that point, we can actually go ahead and get rid of our common factors. So in this case, I'm going to get rid of my 4x minus 5y from the bottom and from the top, and I'm left with 4x plus 5y divided by 2. For the second example, we're dealing with a simple trinomial where a is equal to 1. So we're looking for two numbers that multiply to give us negative 6 and add up to give us negative 5. So in this case, we have x minus 6 and x plus 1 as our factored form. On the bottom, we see another difference of squares here. So I can factor this as x plus 6 and x minus 6. Before we get rid of any of our common factors, we can look at our two NPVs. We can see here that x plus 6 cannot equal to 0, so x cannot equal to negative 6. That's my first NPV. And for my second NPV, I have x minus 6 cannot equal to 0. So x cannot equal to positive 6. So x cannot equal to positive or negative 6. Looking at our common factors now, we can get rid of them. So I can get rid of x minus 6, and we are left with x plus 1 over x plus 6. Some people might be asking, well, do I need to leave the brackets on once I simplify by getting rid of my common factors? No, it's okay just to leave it like this. We can tell that this is just going to be a binomial up top and a binomial on the bottom. Whether or not you have your brackets on there, it's not a huge deal. For these next 4 questions, you can go ahead and pause the video and then unpause once you're done to check your work. Make sure that you're ensuring that you find your NPVs before you get rid of common factors. So at this point, you might be wondering, well, why do we even bother trying to simplify rationals? Well, the simple answer is that it's a lot easier to work with something that looks like this, x plus 1 over x plus 6, rather than working with x squared minus 5x minus 6 over x squared minus 36. Because when we're trying to evaluate certain expressions by substituting in certain values, it's going to be a lot easier for us to work with a simpler expression. Now, for those of you in high school, again, once you move into higher level math, such as your first year calculus courses, you actually won't be able to use any graphing calculators. You're just going to have to do a lot of this by hand. So being able to go from this right here into this is a really valuable skill, and it helps cut down the amount of work that you actually need to do later on. So when we're multiplying rationals, we're going to once again look back at multiplying fractions. So if we're looking at these two, or this example here, if we have 5 and 4, 5 times 4 gives us 20. And we're going to divide that by 24 times 45, which gives us 1080. And pulling up our handy dandy calculator, we can go ahead and cheat a little bit. We've got 20 over 1080 gives us this decimal. I'm going to press FD and we get 1 over 54. So we can use a calculator for something like that. But if we want to do a little bit more legwork, we can see that we can divide both the top and the bottom by 20 as well. So divide the top by 20 and divide the bottom by 20, and we would end up with the exact same answer. So remember, we can get rid of different factors. It doesn't matter if they're both on the top and bottom of the same fraction. We can just get rid of common factors, even if they are diagonal from each other. Now, when it comes to rational expressions, just make sure that we are factoring first in order to find those common factors, and we must need to find our NPVs before you get rid of those common factors. So let's work through a few different examples where we are multiplying rationals together. So for this first one, I'm going to show you two different ways to work through this. First of all, one where you just kind of lump everything together, and another one where you get rid of things as we go along. It just really is up to you to figure out which one suits your learning style a little bit better. So for the first one where we kind of lump everything together, let me go ahead and do this. Do this in blue. So for the first one, let's go ahead and multiply our tops together. 12 times 20 gives us 240. I have x squared and y up top. Now on the bottom, I've got 16 times 9, which gives you 144. Then on the bottom, I have x cubed, y cubed. So before we go any further, let's go and identify our NPVs. So really, since we have a monomial on the bottom, we're just looking at our two variables. So typically we just have x cannot equal to 0. If I put an x in the bottom, it makes the whole thing equal to 0. And y also cannot equal to 0. So to simplify our coefficients here, you probably wouldn't guess, but we can divide the top and the bottom by 48. So that leaves me with a 5 on the top and a 3 on the bottom. And now I have an x squared over x cubed. So visually what that looks like, if I have x squared on the top and x cubed on the bottom, I'm really just getting rid of two x's on the top and 2 from the bottom. So I'm really just left with a single x on the bottom there. Doing the same thing for the y's, I get rid of 1 on the top and 1 from the bottom. And now I'm left with a y squared on the bottom. So I have 5 over 3xy squared as my final simplified form. Method number 2 involves us just doing a little bit of simplification as we move along. Again, if you aren't really keen on kind of putting together everything all at the same time and you want to work with smaller numbers, then that's perfectly fine as well. It just really is up to you. Typically, I like to do this if I'm teaching in front of a class and I don't want to reach for a calculator. So really all I'm doing in this case is I'm just trying to look for factors that I can get rid of from both the top and the bottom. So you can see here, I've got a 12, and maybe what I'll do is I'll work with the 4s first. Between the 16 and the 20, I can actually divide both of these two by 4. So from here, I've got 20 on the top, divided by 4. I'm just going to get rid of that. Divided by 4, it gives me a 5. I divide this by 4, and it gives me a 4. And what I can do now with the 12 is I can actually get rid of this or rewrite it as 4 times 3. And then this now allows me to get rid of a 4 on the top, a 4 on the bottom, because I can divide both 3 and the 9 by 3. I can get rid of the 3 here, and this is now a 3 there. So we can see that the 5 and the 3 are all that's left over in terms of our coefficients. And now I can just work through the question exactly the same as I did previously. I get rid of 2 x's on the top. I get rid of 2 on the bottom, so I'm just left with a single x. And then I have a y on top that I get rid of, and I get rid of 1 on the bottom. Instead of y cubed, I now have a y squared on the bottom. So again, it just really is up to you what you'd prefer to do. Obviously, you end up with the exact same answer. It's just whatever is more comfortable for you. If you aren't so great at mental math, I would probably just stick with something like this, because there is a pretty high chance of you making a mistake if you work through the question like this. And you can always rely on your calculator as an example. If I go 240 over 144, and I just turn that into a fraction, and I get 5/3 as well. So either way works. It's really just up to you. So for this next question, I'm going to look at the NPVs first, because it looks like they're already in factored form here. So from x minus 3 cannot equal to 0, I get x cannot equal to positive 3. And then I also get x cannot equal to 0 and y cannot equal to 0 from this rational. So from here, let's go ahead and get rid of some of my common factors. So here I've got a 10 on the top and a 5 on the bottom. I can just divide this, and I end up with a 2 up top. Now I can get rid of some of my other common factors. I get rid of my x minus 3 on top, x minus 3 on the bottom. I get rid of a single y on top and a single y, get rid of a single y on the bottom. And once we clean that up a little bit, I've got a 2 times 2, that gives me a 4. I still have that y that's on top, and I still have an x plus 3 on top. And then on the bottom, the only thing that's left over is just that x. Once again, for this next one, I already have these all factored out. So I get 2 NPVs. X cannot equal to 0 coming from the 2x. And from here, 5 minus x cannot equal to 0. So that's my first one. And then my second one, I get x cannot equal to positive 5. So I get 2 NPVs for this equation here, or this expression rather. So what we can do here is I can factor this out as x plus 2, x minus 5. I have the 2x on the bottom. I'm multiplying this by x minus 3 up top. And then I can factor out the negative on the bottom. So I can factor this out as negative x minus 5, like we did in previous examples. And we can get rid of some of these common factors. So I can see here that I've got an x on top and an x on the bottom. I can get rid of my x minus 5, and we are left with x plus 2, and then times x minus 3. And then on the bottom, I have a negative 2. And that's it, just a negative 2 on the bottom. You could rewrite it so you have the negative up here as well, and then a positive 2 on the bottom. It's really up to you. Actually, I like that better. Let's just move that negative up here. Again, numerically, it doesn't really matter so much. Typically, we just like to have the negative up top, typically. For this next one, we'll have to do a little bit of factoring. We can see here that we've got a difference of squares on top, so that's y plus 3, y minus 3. On the bottom, I'm going to factor out an x. So I'm left with an x squared minus 1. We're going to have another difference of squares here on the bottom. Let's continue by factoring out an x from the top. So I'm left with an x minus 1. On the bottom is just y plus 3. Before we can find our NPVs, we need to factor out this difference of squares here. So I have a y plus 3, y minus 3 over x, x plus 1, x minus 1. And then everything else stays the same. So I'm going to have a few different NPVs here. We can see that we have x cannot equal to plus or positive or negative 1 from right there. It can also not equal to 0, and it can also not equal to negative 3. Once we found our NPVs, we can start getting rid of those common factors. So we see that we've got an x minus 1, x minus 1. I've got an x that I can get rid of on the top and the bottom. I can get rid of the y plus 3, y plus 3. And finally, once the dust kind of settles, we end up with y minus 3 over x plus 1. For this last one, it's a bit of a challenge question, so you can pause the video and then unpause to check your work. Now, when it comes to dividing rational expressions, we're going to follow the exact same process as we do when we're dividing fractions. So just to recap here, if we have 8 over 12 divided by 4 over 9, what's going to happen is we're going to keep that 8 over 12 exactly the same. You guys might have heard of the process as keep, change, flip. We're going to change this division sign into multiplication. And we're going to flip our fraction. We're going to change the numerator with the denominator. And now this is being multiplied by 9 over 4. So for us, this now gives us 72 because 8 times 9 gives us 72. And 72 over 48 is the fraction we end up with. We can divide both the top and the bottom by 24, and we end up with 3 over 2. So when we're dividing, we just need to be really careful with NPVs. So we can see here that we've got 2 of them to start off with. First of all, we've got B and D. So we get B cannot equal to 0 and D cannot equal to 0. But once we go ahead and flip, right, our second fraction, we can see now that C is on the bottom. So we get C cannot equal to 0. So once we actually finish multiplying, we get 3 NPVs. B cannot equal to 0, C cannot equal to 0, and D cannot equal to 0. So you can see that the steps that we want to follow are we're going to factor each of our questions first, figure out the NPVs. Then when we change our operation and invert your second fraction, we're going to have to find the new NPVs, and then we simplify. So starting us off, let's find the NPVs first. So I've got a few of them. I've got M cannot equal to 0, N cannot equal to 0. So I've got my 2 first. We're going to simplify, or rather, we're going to multiply by the reciprocal. So again, we're changing our sign here. So now instead of division, it's multiplication. And we're going to change the 9xy with the 10mn to the power of 4. So 10mn to the power of 4 comes up top, and 9xy is here on the bottom. And now we have 2 new NPVs. X cannot equal to 0 and Y cannot equal to 0. So here we're going to get rid of some common factors. So starting with our variables, I'm going to get rid of 1x on the top, 1 on the bottom. I get rid of 1y on the top, 1y on the bottom. I get rid of 3 n's from both the top and the bottom. So instead of a 4 now, I just have a single n. And get rid of an m from the top and the bottom. So let's see what we end up with before we go any further. So I have 6 times 10 gives me 60. I still have an x and an n left on top. And then from the bottom here, I now have a 5 times 9, so that gives me 45. From here, I can divide the top and the bottom by 15, so that gives me 4xn over 3 as my final simplified answer. For this next one, we can see that there's a lot of factoring that we're going to need to do. So let's go ahead and factor before we look for our NPVs. So the top here, we have a difference of squares. X squared minus 16 can be factored as x plus 4, x minus 4. On the bottom here, I need two numbers that multiply to 12, add up to 7. So I have x plus 4, x plus 3. I'm still just going to keep this division sign first because I want to figure out what my NPVs are from here. So I can factor out a 2 from the bottom here. And up top, I've got a -8. So two numbers that multiply to -8 and add up to -2. So I have x minus 4 and x plus 2. So here I can go ahead and figure out what my NPVs are to start us off. So I've got from the first factor, x plus 4, x cannot equal to -4. From my second factor, x cannot equal to -3. And then from the x plus 2, x cannot equal to -2. Once we're here, we can start to flip our second fraction. So I'm just going to keep everything in our first fraction exactly the same, so we're not getting rid of any common factors just yet. I'm going to switch the top and the bottom here. So the 2x plus 2 goes up top, and the x minus 4x plus 2 goes on the bottom. And we can see here now that we have potentially two more NPVs or two new NPVs. So in this case, we get x cannot equal to +4. So x cannot equal to +4. And we just have another repeating NPV, x not equal to -2. So we can just leave those four as our NPVs. Now we get to the fun part where we can get rid of common factors. So I see an x plus 4 on the top, x plus 4 on the bottom, x minus 4 on the top, x minus 4 on the bottom. I see an x plus 2 on top, x plus 2 on the bottom. And what's left over, we'll have a 2 on the top divided by just an x plus 3 on the bottom, and we have our four NPVs right there. At this point, you can pause the video and try out these next two problems. I'm just going to write the answers down along with the NPVs. If you have any questions about the work involved for these two, you can just go ahead and comment down below, and I'll do my best to answer as best as I can. Moving on into adding and subtracting rationals, we just need to make sure that we're following the exact same methods as if we were just adding fractions. So you can see here in this example, if we have 1/9 plus 5/9, we simply add our two numerators together. 1 plus 5 gives us 6. The two numbers, or our denominators rather, stay the same, right? So the 9 just stays as the 9. So we end up with 6/9, which can be simplified into 2/3. If you're a little confused about why that happens, let's think about a pizza as an example. If I take half of a pizza and I add another half of a pizza, I have two halves. So those two halves give me 2/2, which simplifies to give me 1. It really wouldn't make a lot of sense if I added 1 plus 1 together to give me 2, and 2 plus 2 together to give me 4. If I take 1/2 plus 1/2, that doesn't give me 2/4. 2/4 again is the same thing as 1/2. I don't have the exact same answer. So 1/2 plus 1/2 has to equal to 2/2, which is the same thing as 1. So I can't actually add your denominators together. So in these three examples, we can see that all of their denominators are the exact same. So we don't need to worry about finding lowest common denominators just yet. So before we get started, we can find our NPVs. So for example 1, x cannot equal to 0. And because, again, all of our denominators are the same, we're just going to simply add the numerators together. So 5 plus a, and then minus 7 goes on top. And this is all divided by 2x. And all that's left over, 5 plus or 5 minus 7 gives me a negative 2. So I have a minus 2 over 2x, and I can't simplify anything in this case. For the second example, again, my NPV happens to be x cannot equal to 0. We can go ahead and add or rather subtract our numerators, so 6x plus 7. And this is where it gets a little bit tricky. So I'm going to subtract the entirety of whatever's on top. So I'd recommend that if you're a little bit uncomfortable with fractions, you can go ahead and subtract everything up top here and leave those in brackets. And we're dividing by 5x squared. And the reason why I would suggest that is now we can think of this as we are subtracting a 2x, so that's minus 2x. And at the same time, we're also subtracting a negative 19. So when you subtract a negative number, we are now adding 19, and we're now dividing by 5x squared. From here, we can combine our like terms. 6x minus 2x gives me 4x. 7 plus 19 gives me plus 26. And we're dividing by 5x squared. At this point, what you want to do is you want to get into the habit of also factoring out the top if possible. So we can see here that I can factor out a 2. So I now have a 2x plus 13 inside of the brackets there over 5x squared. And what that does is if the bottom also happened to be divisible by 2 or factorable by 2, and actually get rid of the 2 up top and a 2 on the bottom. But since nothing really factors out at this point, I can just leave it like that. For this third example, again, our denominators are the same, but we just have single NPV x cannot equal to positive 2. So we start off by adding our first two numerators together, x squared plus 3x. And then I'm going to subtract 10. So now we'll have all of that over x minus 2. What we can do on top is we can factor this as x plus 5, x minus 2 over, and we'll do this, x minus 2 over x minus 2 on the bottom. And we can see here that I have a common factor of x minus 2 on both the top and the bottom. And we are simply left with x plus 5 as our simplified rational. Now, the tricky part about this section comes when we are looking at rationals that have different denominators. So if this is the case, we need to figure out what the LCD is, or the lowest common denominator. Write your equivalent rational expressions over your lowest common denominator, then add or subtract the numerators, and then simplify if possible. Now, when it comes to finding the LCD of smaller numbers like 2 and 4, we can see that it's pretty quick for us to see that in this case, it's going to be 4. For 2 and 3, it's just going to be 6. But for something like 10 and 15, which is still going to be pretty straightforward, we know it's going to be 30, we can actually use our calculators to help us out. So to start us off, let's look at the TI-84 first. In order to find the lowest common denominator between 10 and 15 as our example, we're going to hit the math button right here. And once we're in this menu, we're going to scroll over to numbers. So we're going to hit right to scroll there. And we're going to go down to number 8. So we can either hit the number 8 or we can just scroll down to 8 right there. And we see LCM, so lowest common multiple. Whoops, scrolling way too much. This emulator is a little bit laggy. So let's go back to number 8. Press enter. And because we're looking for 10 and 15, I'm going to go ahead and type in 10. You need to make sure that you put a comma there. And then we're going to close it off. So the lowest common multiple between 10 and 15 is 30. Now, I realize that on my Casio, I can't actually show it to you because this emulator is a little bit old. But really what's going to happen, maybe I'll exit out of this. Oops, I will exit out of this portion here. So from this screen, what you'd have to do on a Casio, I think for the 9750, I believe, is the model that most of you guys have right now. We're just going to hit the option button, and you're going to see these options pop up. We're going to hit F6 to go over to the right. we're going to hit number. So for my emulator right now, it doesn't really show the proper functions. I don't actually have this, the LCM function on this calculator, but there would actually be another arrow right here that you can hit. So you'd have to hit F6 and you should see a num. So NUM is going to pop up right here. You'd hit F4 and basically you're going to have the exact same thing pop up as you do on the TI-84. You're just going to hit 10 and then comma. Your comma in this case can be right here. 15, you're going to close off the bracket. It would automatically put LCM bracket and then you'd have 10, 15. And once you do that, you would end up with 30. Now, the nice thing about the Casios is even after you press enter, you would still have, your LCD function stay right here. Whereas for the TI-84, if you were to do it again with a different set, you can't automatically just select it. You'd actually have to go back into this menu, go to number, press number 8, and then start off again. I mean, I guess you could also just do this. You can scroll up, press enter, and then just change these numbers as well. But again, depending on what types of numbers you're using, it might just be easier just to kind of reset it again. So let's work through a few different examples together. First of all, in this case, we can already look at our NPV. So our NPV in this case for number 1, we get x cannot equal to 0. We're going to look for the LCD. And again, because our coefficients, we have a 2 here, we have a 4 down here. Our LCD between 2 and 4 is just going to be 4. And because we also need an x as well, we can go ahead and write our LCD. Oops, let's make that neater. LCD is just going to be 4x. So our goal here is to figure out what do I need to multiply the top and the bottom of each fraction by in order to get that 4x. So let's start with the one on the right. Down here, we're just going to need to multiply this by x. So 4 times x gives me 4x. And then since I multiplied by x on the bottom, I also need to multiply by x on the top. Now for the left-hand side fraction, because I need 4x, I just need to multiply the bottom by 2. And I'm also going to multiply the top by 2. So this leaves me with 6 over 4x plus 5x squared over 4x. And because I have the same denominator, I can just simply add 6 plus 5x squared. So 6 plus 5x squared over 4x. There's nothing that I can factor out from here, so I am done. For question number 2, my 2 NPVs, I have A cannot equal to 0 and B cannot equal to 0. Looking at the LCD between 2 and 3, my LCD is going to be 6. And because I also need an A and a B, I'm just going to go and put those in there as well. So looking at the left-hand side fraction, in order to get 6AB, I need to multiply the bottom by 3B. And what I do to the bottom, I also do to the top. And then for the right-hand side fraction, I need to multiply by 2a on both the top and the bottom. So here I'm left with 3b times 7 gives me 21b. And this is all over 6ab plus 10a over 6ab. And now because I have the same denominator, it's all over 6ab. And I add 21b plus 10a. This next one, we know our NPV is just going to be y cannot equal to 0. And then looking at our LCD, a little bit trickier, but again, we know that the LCD between 10 and 15 is going to be 30. And then between y and y squared, I'm going to need a y squared. So to get us to this LCD, I'm just going to multiply the bottom here by 2, multiply the top by 2. And to get the left-hand side fraction to 30y squared, I multiply the bottom by 3y and the top by 3y. So we're left with 21y. Maybe I'll make that neater, 21y over 30y squared plus 2 over 30y squared. So when we clean this up, we'll end up with 21y plus 2 divided by 30y squared. For question number 4, we want to look at our NPVs first. So we get x and y cannot equal to 0. So x cannot equal to 0 and y cannot equal to 0. Let's identify our LCD next. So we have a 4 that we're going to need, and we're going to also need an x and a y. So for us, that means this bottom part needs an x, and the top needs to be multiplied by x as well. For the second fraction, I'm going to need a 4x on the bottom, which means I need 4x to be multiplied on top. And then for the bottom of this first fraction, I need to multiply by 4y, and I multiply by 4y on the top as well. So what does this leave me with? I have 12y squared over 4xy plus 28, in this case, x squared over 4xy. And I'm going to subtract all of this here. So I'm going to subtract, after I multiply this x in, so I'm going to subtract the 2x squared plus x, and that's over 4xy. And what this leaves me with, once I put everything all over 4xy, I'll have 12y squared plus 28x squared. I'm subtracting 2x squared, and I'm also subtracting an x up top. So once I simplify everything, I end up with 28x squared minus 2x squared. That leaves me with 26x squared. Then I have plus 12y squared minus x, and that's all divided by 4xy. So I'm going to stop the video here as we are getting into the feature film length territory. In the next video, we're going to continue on with adding and subtracting rationals, and we're going to focus in on binomial and trinomial denominators that are not the same. And then after that, we're going to move into solving rational equations. Once again, I hope you learned a thing or two from this video. If you have any questions, feel free to ask them down below. Thanks again for watching, and I'll see you in the next video.